I'm Dinesh Raghu. I'm a senior researcher at IBM Research. I lead the conversational AI team there, and our team mainly works in the intersection of large language models and conversational AI. I've been with IBM for about 12 years now, and I did my master's here at IIT Delhi in the electrical engineering department, and I did my PhD also here in the computer science department with Professor Mosam. So today I'll be talking about how can we fine-tune large language models in an efficient manner. Specifically, I'll be discussing the parametric efficient fine-tuning in large language models. Right. So before we jump into the PEFT techniques, let's first just look back to see how things were before the large language models came into picture. Right. So typically, this was a transfer learning era where when you have a large unlabeled corpora at your disposal, you use them to sort of get a sense of the world knowledge by either learning word representations or contextual word representations or sentence representations, and then use them and transfer this knowledge to a task-specific case. Now, so hence it had two phases. There was a pre-training phase where you just use the unlabeled data and you develop some world knowledge. And then you have the fine-tuning stage where you transfer the world knowledge that you had using pre-training, but then use your task-specific data and fully fine-tune the model, right? And there were different ways of fine-tuning them. Fully fine-tuning was one such technique. Or you can add augment the pre-trained model with additional layers and then fine-tune them as well. So there were multiple ways in which people fine-tune. Now, what changed during the LLM era is that the models became more aware and were better capable of how they model the world knowledge, right? So initially there was just pre-training phase, but now we have instruction fine-tuning and alignment phase, which I hope it has already been covered in this class, right? So there is slight change in how we leverage the unlabeled data, but the instruction tuning and alignment does come with some labeled data, but it's general purpose, right? Again, it teaches the model world knowledge. It is not teaching it any specific task. Now, once we have a model this way, then the first way in which people started leveraging such a large language model was to simply do in-context learning, right? So by in-context learning, what we mean is that whatever knowledge that you want to feed the model about the task you want to solve, it's sort of fed into the input prompt, right? So sometimes people specify a detailed set of instructions of how to solve the task. Sometimes people feed instructions along with some examples of how the input-output pairs so that the model learns them better, right? So this was the beginning of a new era where we were able to solve like good number of NLP tasks by simply using in-context learning, right? Now, the reason why this is really useful is because hosting or serving LLM is very expensive and it requires a lot of hardware and compute, right? So not everybody would be able to who wants to leverage LLMs would be able to host it. So if it has been hosted in a certain by a certain provider, then it's easy for people to make it useful for their task by simply doing in-context learning by calling them through APIs, right? So this was the main advantage of how transfer learning worked in LLM era. Now, so let's see, like why aren't people happy with just in-context learning, right? So given that LLM knows a lot more about the world, why are we not happy with just in-context learning? So firstly, relative to what people did earlier, which was full fine-tuning, prompting was not that great. So if the task is very critical and you need really good accuracies, then prompting typically does not get you there. You will have to do full fine-tuning of the models that you have to get to the best performance. But why does prompting have poor performance, right? So there are two main reasons. One is that there are certain things in the prompt engineer's control, and two is there are some things that the LLMs assume for themselves, right? So so if the prompt engineer does not do a very diligent job of defining the task, then it is one reason why it would lead to poor performance. But then there are certain academic benchmarks where a lot of researchers try, and they still are not able to get good numbers as good as a fully fine-tuned model, which is much smaller than a big model, right? So the reason for that is that when the large language model learns, there are certain assumptions it makes, and there are only certain things that it can comprehend, right? While we know it is good, but it's hard to know what really goes on in the back, right? So when certain things don't work, it could be because the model has not learned some aspect of certain domains, or it could be that there are certain assumptions that the model is making that we're not able to figure out what those assumptions are, right? So there are a lot of reasons why prompting can take you only to a certain extent. Now, the second problem with prompt engineering or simply in context learning is that these prompts are extremely sensitive, right? Even if you earlier when the LLM started, even missing a simple proposition would create a very different, would result in very different performance. But even when you have a really good models, and typically when your input output pairs are, when your input is pretty long or your output is pretty long, right? The order in which you put them in the in-context learning also affects the accuracy that you get, right? So again, why is this a big problem? Because maybe there is if you're really concerned about the task, or if you're really particular about it, then you can always dedicate people to sort of come up with the right way to make everything work. But the problem is, once, let's say, like few months back, Llama 3.1 came, which was much more capable of than Llama 3, right? Now you'll have to do everything from scratch, because the assumptions that are made by Llama 3 and Llama 3.1 may not be the same. The knowledge that went into training may not be the same. So every time a new model comes, then you'll have to do everything from scratch. And whatever you did earlier may or may not hold. Like most likely it doesn't hold. And thirdly, so there is always an issue about like what the model really infers from the prompt you give it, right? So this also happens with any machine learning algorithm, right? When you have really deep networks, you really don't know what the model learns from the data you provide. But here there is a two-hop thing, right? You are providing certain instructions and very small subset of examples, and the model also has a lot of knowledge inherently built in with it. So there may be a big gap between what you say and what the model can understand, and then there can also be a gap between like what it learned from the data that you provide, right? So there are a lot of variability, and people have also found that like even providing weird in-context examples works for certain tasks, right? Which makes no sense, because ideally when you provide prompts in a very unrealistic manner, the model should not work. But still the model learns to ignore those. So we don't know whether it's ignoring those signals. We don't know whether it's learning something spurious from that signal. We don't know when the model will fail and so on, right? So this lack of clarity makes it difficult for people to trust models and then use them right away, right? So far the first three items that I talked about are more from like the linguistic standpoint, or what the model can comprehend and what it cannot, right? But the last part is more system, right? It's just that if you use up a lot of your prompt space for just giving instructions and in-context examples, then it simply increases it increases the latency that you get with your model, and also resources and throughput and energy and so on, right? So specifically, most of the real world use cases are not going to be like input-output pairs of length, let's say 20 tokens or 25 tokens. Right? For example, if you want to do reading comprehension or summarization, it's going to span too many tokens, right? So and if you have a very specific way of summarization, right? So let's say news article summarization. Maybe you want to summarize scientific news in a certain way. Maybe you want to summarize opinion piece in a certain way. Maybe you want to summarize sports-related events in a certain way. Now, you'll have to provide all these instructions in a detailed manner. You have to provide in-context examples of all these things. So this would take up considerable amount of space, and that would result in like inefficiency in how you use the hardware and stuff, right? So these are the downside of in-context learning. So now let's see, like, okay, if in-context learning has these many problems, then let's start doing full fine-tuning, right? Because this has been what people have been doing for a really long time now. So why can't we do fully fine-tuning, right? So let's say that you want to fine-tune Llama 8 billion model, right? Now, it might end up taking 16 gigs of memory if it's in FP16, if all the weights are in FP16. But when you fine tune a model, it's not just the amount of parameters that the model has determines how much memory it needs, but rather it also needs space for optimizer states, storing gradients, storing forward activations during your forward step, and also a lot of temporary memory here and there. And this sort of so there are different ways in which you train the model. There are like full precision training, mixed precision training, low precision training. So like if you consider multiple all these different types of training, then you end up needing around 12 to 20% of trainable parameters. That's the amount of memory you need, right? So let's say you want to fine tune a 175 billion GPT-3 model, right? It's going to take like insane amount of memory, and not everybody who wants to use LLMs or has the capability to host an LLM would have enough infrastructure to fine tune an LLM, fully fine tune an LLM, right? So then it will become difficult for research to progress ahead, and also like in general accessibility also reduces a lot, right? So this is one of the main reasons why people don't want to do full fine tuning of large language models. And the other main reason is storage, right? So let's say like your checkpoint is 350 gigabytes, right? Every time you have a small task to learn, then it becomes really tedious to save a checkpoint for each task you have, and it becomes even more tedious to serve them, right? So now if you had to serve only one LLM in an in-context learning setup that serves all tasks, then you just need one copy of it, right? You may need, let's say you need 8 GPUs in a node, and then you can serve them. But now if you have, let's say, 5 or 6 tasks, right? And specifically if you are working in a company that infuses LLM in a lot of applications they have, then we can't host like 10-15 LLMs and without leveraging the entire throughput, right? Because if it's not efficient, then again it's a waste of energy, and again it's expensive. So these two are the main reasons why people don't want to do full fine tuning, but there are other reasons as well, right? So one other reason which I've not listed here, which is also one of the common reasons, like even if you have enough hardware, let's say, right, you have insane amount of hardware within your organization, and you don't have to worry about storage. Then of course, if you have a lot of hardware, then you can host how many ever LLMs you want, right? But the problem is, how much training data do you need so that the model doesn't overfit, right? If you have 175 billion parameter model, right, and you just have, let's say, 1,000 or 2,000 examples, the model is going to completely memorize all the 2,000 examples, right? And once it memorizes 2,000 examples, your training accuracy will be really high, and your validation may not be that great, and you will encounter this problem. Like the whole notion of transfer learning gets lost, right? That was the motive behind fully fine tuning. But then then imagine the amount of data you might need, right, to actually get a model that doesn't overfit. That's going to be insane, and it's going to be really hard to collect that much data, right? So that is also one other reason that people would want to refrain from doing fully fine tuning, right? And now comes the parameter efficient fine tuning. So now on one end you have in context learning, on the other end you have fully fine tuning. Now people are trying to figure out what if I freeze most of the parameters in my network and only train a very small subset so that I don't face all the issues that I face with fully fine tuning, and at the same time I can mitigate some of these issues that I face with in context learning, right? So that is the whole crux of parameter efficient fine tuning. So here as you see, like if you have to train a QA model on top of LLM using PEFT, then you would get a very incremental number of parameters compared to what the LLM already has, and that would represent everything that's needed to learn the task. And same thing goes for summarization, and same thing goes for classification. And so this is the crux of PEFT. And so now the advantages are going to be like, we're going to borrow some disadvantages from in context learning and fully fine tuning and sort of put it here. So of course, like I mentioned, the first issue with fully fine tuning was the hardware requirements, right? So you require 12 to 20 times the number of trainable parameters, the memory of that amount to sort of support training, right? So now if you reduce the number of trainable parameters, of course your optimizer states are going to come down, your gradients are going to come down, activations may remain there, but a lot of these temp usage may come down, and this reduces the amount of memory that you need drastically, right? So now, so which means like you can use fewer GPUs to train your model, right? And one other thing is that since you're working at a lower parameter space and most of your world model is frozen, the model learns to sort of map world knowledge to your task and then converge faster, right? So this actually helps the model. This also saves in GPU time. Like you learn models faster than what you would learn by fully fine tuning. Of course, the obvious next thing is that hardware requirements is lower. So which means not only less memory, but also like many institutions and organizations who started using GPUs during the deep learning era and now are slowly moving towards the LLM era, like they can still work with V100 Tesla models, or they don't necessarily have to have the A100s with 80 gigs or the H100s to sort of fine tune. They can work with older versions of GPUs with less memory and they can still get a lot of work done, right? So that is a very big advantage, because a lot of these older machines which consume less power are idle, right? And this is one way of effectively using them. And of course, like I said earlier, one of the issues with fully fine tuning is that you have such large parametric space to leverage during your learning process. You end up overfitting and memorizing all the training examples. So now if you don't have so much capacity to begin with, then the likelihood of overfitting reduces a lot, right? Again, I'm not saying that overfitting goes away completely. It depends on how many parameters you let the model sort of use during training. But again, the likelihood of overfitting reduces considerably. Now, in addition to that, there is this phenomena called catastrophic forgetting, right? So catastrophic forgetting is a process in general to any machine learning model. Let's say that you initially started to teach the model task A, right? So now the model has learned task A very well, and now you want to teach the model task B, right? So now, how good would the model be in task B? Let's say you're working in a pre-LLM era. Let's say you're fine-tuning BERT. You initially fine-tuned it for classifying, let's say, finance versus tech classification, and now you want to teach it spam detection or something, right? So how many people believe that spam detection, if the spam detection was the task B, how many people believe the task A would still be doing good after you teach the models task B? Right? So it's not going to learn, right? So now imagine this with large language models. It knows the world knowledge, right? You have taught it so much during the pre-training, fine-tuning, pre-training, instruction tuning and alignment stage, right? Now you teach it a very simple task and it's going to forget everything that it gathered so far, right? You don't want that to happen. So this, most of the PEFT techniques are good in this type of transfer learning, right? They don't typically forget the world knowledge, which means that if you teach a task with a certain domain, it is very likely to generalize to a new domain, right? If you teach it spam detection in, say, IIT Delhi, now if you move to US where maybe the spammers are different or the type of language people use is different, it is very likely going to work, right? It's not going to fail. And finally, of course, the obvious thing is that it requires less storage because the number of parameters that you store are less. So obviously, you only have to save the incremental weights that you've learned, and you don't have to store the entire copy of LLM again, right? So it's going to be, it needs just very little storage. Now, with these advantages and the context of why we need PEFT and why it is useful, let's dive deep into a few popular techniques that people use for parameter efficient fine tuning, right? So first, let's talk about the prompt tuning or soft prompting, right? So this was not one of the first PEFT techniques, but I'm starting with this because this is one of the easiest things, and it gives you, and we can build upon it in the remaining of the lecture, right? So typically when you do in context learning, we refer to it as hard prompting, because you write the prompt in the in context setup, and if you don't like the prompt, then you change certain words or you rephrase certain things or you add examples. So this way of modifying the prompt or the in context setup is hard prompting, because humans are involved in doing this, right? So what Lester et al. Thought was that why should we, if we have a large amount of input and output available with us, and it's easy for us to measure how good or bad the output is, then wouldn't it be easier for the model to learn this prompt by itself, right? So all they say is that you reserve certain tokens in your input for certain special tokens called the soft prompt, right? And the only trainable parameters in your model is this task specific prompt, right? Everything else in the architecture remains the same. You don't change any other weights. Everything is frozen. You only change these new tokens that you want to call it as soft prompts, right? And this is what their idea was. And the good part about this idea is that for a specific task, after you complete the learning process, all you need to do is save that soft prompt, right? Which is going to be like orders of magnitude lower than what the LLMs would do, right? So let's say if your tokenizer, so your embedding size is, let's say 4K or something, right? And if you use 5 tokens, this is very marginal compared to the size of LLMs that we have now, right? So that is now, like we know that given the number of trainable parameters is so low, it's one of the most efficient way of fine tuning, like compared to full fine tuning. Now there is also another like really good advantage of soft prompting, right? Which is the multitask serving. Like let's say you're hosting an LLM and you let people fine tune for various tasks, right? And let's say that you have 120 tasks in your organization or for your project. Now, during training, you would have data sets for each of your tasks that you want to learn. And so you will assign certain special tokens for each of your tasks, and then you will start your training process, right? So for example, for task A, you end up training the yellow tokens, and for task B, you end up training the green tokens, and your LLM weights remain frozen, right? And now the good part is during inference, it's so easy, right? You just need to host the base LLM, and when you create batches to feed to your LLM to predict the output, you can just batch in whatever task you want based on what traffic comes in, right? So this is extremely efficient for serving, because it may not so happen that the traffic for your LLMs are going to be that high, right? If you have 120 tasks, right? If it's high, then you of course you have to have separate. You can have a lot of instances of LLM running, but it's easy to scale up, scale down, because you just need the same LLM again. So if the traffic goes down, you can scale down certain hosting, and then you can keep running them for multiple tasks at the same time. So this is one of the biggest advantages of prompt tuning, and this is why most LLM hosting companies they provide you an API to prompt tune, right? Because hosting is so cheap for them. Like even if you, because they charge you per request, right? They don't charge you per time. So their GPUs are anyway running. So it's going to be more efficient for them if they support this type of prompt tuning. Now, so let's look at how does it compare with full fine tuning, right? So the graph in red or orange is full fine tuning, and here the graph in green is prompt tuning, and the graph in blue is simple prompt engineering, hard prompting, right? And the x-axis here is a number of parameters in the model that you're trying to fine tune, right? So right from 10 power 8 to 10 power 10 are the family of T5 models. So they have different sizes of T5 models that Microsoft had trained, and highest one is like 11 billion model, and the lowest one is around 700 million model or something, right? 770 or something. And if you see, there is an additional point on the right for blue, which is prompt engineering, and that point, the last point, which is about 10 power, little more than 10 power 11, is GPT-3, right? Yes. So that's GPT-3. When this paper came out, that was the best model possible for prompt engineering, right, at that point in time. So what they see here is that when you have smaller models, then it's better to do full fine tuning. because it doesn't, prompt tuning or prompt engineering does not give you as much accuracy as what the full fine tuning gives. But as and when you keep increasing the model size, then prompt tuning sort of catches up with full fine tuning, right? So this is, so again, if you see, irrespective of how much you do hard prompting, there is a huge gap even for the 11 billion model. So hard prompting is nothing but, let's say that you want to do classification of spam or not spam, right? So now if I give you access to GPT-4o in the web UI, what would you do? So you would give some instructions, and then you would give some examples of what is spam and what is not spam, right? Some input and output, right? So this is called hard prompting. Like, let's say if this didn't work, this didn't give you a 95% accuracy, then what would you do? Yes, you would change the prompt, right? So that's a tedious process, right? So that this style of creating a solution is what is called hard prompting. So soft prompting is prompt tuning, which is like the model learns it by itself given a small amount of data, right? Okay, so now one of the other findings in this paper is that, which is also slightly obvious, is that if you increase the prompt length, then it improves the performance on the task, right? So this is same as saying, like, if you give a very elaborate instruction, right, or if you increase the number of tokens you use for in-context learning, it is very likely the model would pick up a lot more than what it would if you give it only 1 or 2 words to describe the task, right? So the essence is that way. But the interesting thing they found is that if the number of prompt tokens cross 20 for T5, then they don't see any more improvements. So it sort of peaks at around 20, right? So now one other thing is that, so initializing what should be the weights of these soft prompts to begin with is actually very important, right? If you give it very random initialization, it may not converge to a good point, or it may even take a very long time to converge, right? But if you sort of say, create a prompt using words that are very similar to the, very close to the task description, and then take its embeddings and then post them there, or you take certain words that are very related to the task and then post them there, then that is better. Like, I think that's also an insight that this paper gives. Now, like, one thing that I mentioned in the advantages of PEFT is that it sort of generalizes well to out-domain data, right? So here they test on the task of reading comprehension. Specifically, they take the squad data set where there is a natural language text which describes something, and then there is a question answer following that, right? And this is based on Wikipedia. And here the model is a full fine tuning, prompt is a prompt tuning. So there is hardly any difference between full fine tuning and prompt tuning on the same data set that you trained the model on. But if you see the model's performance on the books data set, which is like very different domain than the Wikipedia, you see that the model sort of generalizes much better, the prompt tuning model, whereas the full fine tuning model does not generalize that well. So they show a bunch of different domains. Some are close to Wikipedia, some are slightly far away. And one of the biggest takeaways here is that the 12.5 improvement on books was actually a very good insight, right? Okay, so now that brings us to the next topic, which is prefix tuning, right? So now, so the number of parameters you use for the PEFT technique has trade-off, right? If you use a lot of parameters, then you're very likely to learn very complex tasks, right? Because your capacity is very high, but your chances of overfitting also becomes high, right? But if you have reduced number of parameters, then your chances of overfitting is less, but your performance can get affected, right? So you need some family of algorithms, and then there's only so much you can do with giving tokens, right? Because if you give 20 tokens and it still doesn't learn, there is going to be like very less likelihood that it's going to get better, right? So we can't just stop with prompt tuning. So then people came up with prefix tuning. So prefix tuning is actually a contemporary work to prompt tuning, right? Both of them got published around the same time. Now, the main difference between prefix tuning and prompt tuning is that prompt tuning gives you those trainable tokens only in the input layer, right? Basically, whatever the embedding layer gives out is where you feed in the special prompts, right? The embeddings of the special prompts. That's the only trainable parameter. Whereas in prefix tuning, you have a small set of trainable parameters in every layer of your transformer, right? So now if you look on the right, so here this is the regular transformer block where you have the multi-edge self-attention, fully connected layer, and then there is a residual connection, layer norm, and then there's again a fully connected network with a residual connection, finally followed by a layer norm. So this is what your regular transformer block looks like. But with prefix tuning, so for now assume this whole thing is a single prefix, right? I'll tell you why we have this particular architecture here. But assume this to have a single prefix. Now if you look at a decoder only model, so basically prefix comes in the beginning, so prefix don't influence each other, but every word that you feed in the input get influenced by your prefix in every layer, right? So that's the sort of crux of this approach. Now so let's see why they have this soft prompt and a fully connected layer here. Like, why do we need that? Like, we could have just used something similar to soft prompts that we used, right? So why do we need this layer? So let's say that we have a prompt sequence of, let's say, 5 tokens or something. So let's call it P, which is all the 5 tokens in sequence, right? P1, P2, P3, P4, P5, right? And let mod P denote the number of tokens in that prefix, right? So ideally, what do we want? We want a function that converts that special token into certain embedding, which can then directly feed into the network, right? And these are the trainable, the f theta is a trainable parameter, right? So now f theta's dimensions have to be that it's sort of like an embedding lookup. For each prefix token you have, you need an embedding associated with it, right? And this embedding, since you're feeding it into the hidden layer, the embedding should be of the size of what the hidden layers that you have is, right? So what the authors found is that if you use this particular f theta to parameterize your prefixes, then it's resulting in unstable training. So what we mean by unstable training is that, let's say, the weights may get changed so high that it sort of breaks the whole training process, right? Your gradients hit the max or it hits 0, or it goes too low, right? So this results in unstable training. So this happens because sometimes that you're trying to learn something with very small number of parameters and you did not put it in the right place where there are certain reasons why we have layer norm, right? So you have to keep these in the right place so that you don't explode things or you don't underflow things, right? So if you don't architect your solution in the right manner, you will end up facing these training issues, right? So you'll have to change code, have some hacks, or change your architecture in such a way so that you don't undergo this unstable training process, because this is a very risky thing to have in your network. Because let's say that after you train for 7 days using like a GPU farm of 100 different nodes, and then you suddenly encounter an unstable training, then whatever you did for so long is a waste, right? So this is something that we should always avoid when you design. And what these guys figured out is that the number of parameters that they have and in the way they have designed it is what is resulting in unstable training. So what they did is that they represented f theta with 2 functions, basically a f theta prime, which has much smaller dimension than the hidden dimension, right? So basically your embedding size is slightly lesser than what you had, but your MLP is very large, right? Let's say that the f theta is of dimension mod p cross, let's say 200 or something, right? And then you will have 200 cross 1024, which is a hidden dimension. So 200 cross 1024 is a very high, larger parameter space than what you would have used for f theta, but then f theta prime is much smaller. So they found this to help in a much more stable training, right? So again, what the advantage here is that during training we might need a large MLP and f theta prime, but once you finish training, you can club both of them together and get back to the same size as what you have for f theta, right? So this is just a hack for unstable training, and I covered this part just to illustrate why design choice is very important, right? Because you will end up having unstable training, which is not something that you want to have in any LLM training or fine tuning. right? So so for prefix tuning, they evaluated their technique on two different setups. One is they used it for a task of text to text, table to text generation, where you have like say in Wikipedia you have a table in the side about the bio and things like that, right? And on the right you have the introduction page, introduction paragraph, which mostly contains everything about what is there in the table. So that's sort of an example of table to text, but there are other variants of it. So they trained a decoder only model. At that point in time, it was GPT-2 for table to text, and then they trained BART for summarization, right? And what they found is that by using only 0.1% of parameters in these models, they were able to get comparable results of full fine tuning, right? For each of the two models separately. Again, the same thing that we saw for soft prompting is that prefix tuning also works well on unseen domain as well, right? So let's move on to adapters. Now, adapters was actually the first PEFT technique that got popular. Like this was in 2019, and after this came soft prompting and prefix tuning. But I just covered them because it's much more easier to discuss, right? So in adapters, what they do is that they add new layers inside each transformer block, right? So and these are called the adapter layers, and each adapter layer has a fully connected layer which sort of projects the hidden dimension down to a smaller dimension, and then there is some nonlinearity, and then there is a fully connected layer that projects back up into the higher dimensional space. So this is the overall architecture of adapters. So please notice here that there is a residual connection here, which is the usual one as what we have in the transformers, but there is also a residual connection here within the adapter, right? So this is to ensure that if you randomly introduce new layers in your transformers, it's very likely you will break everything, right? Because now you have random weights in between. Whatever you learned might go might go for a toss, right? So this residual connection is very important because this will ensure that if this layer is around is let's say a Gaussian, initialize if the Gaussian distribution of a very small variance and zero mean, then it's very likely that in the first epoch you would actually get the same output as what an LLM would give without the adapter layers, right? So this way again your training will be stable. So yeah, so like I mentioned, there are two feed forward networks inside the adapter layer. One here. So this is the first part, which is a down projection feed forward network, and then you have a lesser dimensional space here, and then again you project it back to a higher dimension. This is typically referred to as a bottleneck structure. This is what autoencoders also do, right? Wherein you want to represent your input in a much richer, dense representation, and then you use that to actually represent the input. So this is sort of the same structure here. So why do we need this bottleneck structure, right? Why can't we just keep a single feed forward network or some feed forward network with nonlinearity, right? So the main advantage here is that this reduces the number of parameters significantly, right? So let's say that like your hidden dimensions be 1024, right? And now you're say down projecting it to a value m which is 24. So then in the beginning you might have, like if you did not have this bottleneck structure, you would have had 1024 cross 1024 parameters, right? But now you would have 2 times 1024 cross 24, right? This is like orders of magnitude lower than what you would achieve otherwise, right? And here again, like I mentioned earlier before, like with respect to different types of PEFT techniques, you will have a trade-off between performance and overfitting, right? So similarly here as well, within adapters, this value m gives you that trade-off, right? So you can use this as a hyperparameter, train different variants of the model and see what works and what doesn't work, right? So one of the biggest issue why adapter did not succeed that well is because, like, firstly it's performance. Like people found out better techniques that were much more efficient than them and gave better numbers as well. But the other thing is that there is an inference overhead, right? So you're changing the architecture of the model in such a way, right, that it makes it difficult to remove things and add things. Let's say, like, if you want adapter A instead of adapter B that is already being hosted, it becomes difficult. And secondly, since they are in between layers of existing transformers, it increases latency as well, because you need more time to do, you need more computation, right? So this is an issue with adapters, but most of the other PEFT techniques don't have issue with latency overhead, right? Because they sort of expand it along the sequence length rather than the transformer's length, right? So that is an disadvantage of adapters. So let's see. So again, this is a model that was proposed. This was the first model that was proposed for PEFT. So here, let's look at the graph here. So the blue line here indicates the fine-tuning top layers of BERT, right? So here 10 power 6 would, let's say, indicate first k layers of BERT, and 3 into 10 power 8 would indicate almost all the layers in BERT, right? So this point would be similar to fully fine-tuning, and this would be like as and when you leave out some layers in the bottom, and finally you come to this point, right? So the reason why this was used as a baseline was because people were doing it with BERT, doing this type of fine-tuning with BERT even before adapters, right? You free, like how you freeze word vectors or word to vec or glove embeddings in the bottom and you only train the network in the top. People started doing this with BERT as well when BERT came out. Like, let's not train the whole BERT from top to bottom, because most of the lower layers are going to capture more word level features and more English language based features. Only the top layers are going to capture the task specific features. So people decided, like, I'll freeze most of the things from the bottom and only train the layers in the top. So this was the baseline then, and this is the adapter performance. And here again the x-axis indicates the number of trainable parameters. And the good part here is that with only 3.6% of parameters, it is able to achieve as good performance as full fine-tuning, right? Because full fine-tuning is here, it sort of achieves that performance very early on in that, right? Again, like comparing this with let's say prefix tuning. Prefix tuning came much later, but what adapters can achieve with just 3%, prefix tuning was able to achieve it with just 0.1% of the parameters, right? So if you have a choice between adapters and prefix tuning, you should always prefer prefix tuning, most likely, right? Okay, so this is the last part of the talk. This is it's called low rank adaptation, or LoRA. This is the most for me, this was one of the most interesting papers that I came across, and even the theory behind it is more grounded, and it comes from a long literature of how people had worked from deep learning era till now. So this is this is one of the most popular PEFT techniques that are out there, and you have ready implementations available in Hugging Face, which you can easily use for any LLMs that you have, right? So before going into LoRA, let's look at what people did. How people ended up figuring out LoRA, right? So there was this paper in 2018 that talked about something called rank composition in machine learning models, right? So here, what they say is that, so let's take this equation here, right? So here, what we say is that, let's say that your entire features is d-dimensional. All the trainable parameters in your model, everything, like, don't think of them at separate attention layer or separate feed forward network and things like that, right? Just club everything together and then create one big vector, like insanely long vector, right? So ideally, when you do fine tuning, what are you doing? You're going to take that vector at state 0, and you're going to use your examples, compute loss, figure out something, and then finally you will come up with an increment on those weights, right? And then once you add these things up, you end up getting a fine-tuned model, right? This is what you do. Now, what this paper said is that you don't, for every task, you don't need that many dimensions, right? Maybe for some tasks, you just need very few dimensions and the model will learn it, right? So what they said is that if you have a random projection matrix, Okay, this is randomly initialized and fixed. Okay, we are not going to train it, right? Now there is a certain d-dimensional vector. The dimension of P is capital D cross small d, and for a certain d which is much lesser than small d, much lesser than capital D, there exists a theta d which will achieve same performance as theta tau of d, right? And this value d depends on what is your base model, how capable it is, and what is your task at hand, right? If you have a very naive base model, even for small tasks you might need a big d, but if you have a very capable model and your task is simple, you might need a very small d, right? So it depends on the combination of both. So now they define something called intrinsic dimensionality. What it says is the value of small d that gets you 90% accuracy or performance as your entire full fine tuning is called the intrinsic dimensionality of that particular task, right? So that's what they define as intrinsic dimensionality. Now this was in general made for deep networks, right? But then in 2021, people investigated this in the light of large language models and specifically for NLP tasks, right? So while I mentioned that Lee et al. What they did was they considered the trainable parameters as one long vector, right? That did not take into account the structure of transformers, right? Because there is a repeated structure and there is a layer-wise structure. So maybe the structure will help you do things with much, the expressivity of such a repetitive network is not leveraged in computing the intrinsic dimensionality, right? So these guys came up with a way of measuring intrinsic dimensionality which takes into account this structure. Again, this is not it's not the best way of doing it, but still they figured out that something is missing and we need to take it a little forward, right? Now, the reason why they did that or they thought about in that direction is because it was almost impossible to measure intrinsic dimensionality for LLMs, right? Why? Because let's say you want to do it for BERT, you need 1 terabyte of memory, right? Because the projection matrix, because of the computational, how you do the computation and how you factorize the capital P matrix. So even if you use the best implementation possible, you still end up requiring a lot of memory, right? So they were not even able to figure out how to use it. So that's when they came up with this structure aware technique. What they said is that I will do it layer wise, right? I will represent the theta layer wise rather than having the entire network. If you have 24 layers, then you divide them into 24 different vectors, and P, the dimensionality of P comes down drastically now, right? And then there is also a scaling factor that they add for each update, and these scaling factors are different for different layers, right? And so if you add everything up, the lambda i's and the thetas together, they will you will get a d-dimensional vector, right? So the m is removed there because m is the number of layers we have, and there is going to be a lambda I for every m. So the total number of parameters that you will end up training would be exactly m, right? But again, even this sort of is a little difficult because the models grew insanely higher after BERT, right? So now even if you use the same technique, again you will end up running out of memory for the other case as well, right? Okay, so here, so in the previous equation, what we had is theta d is the initialized value of the first, at the 0th epoch, what was theta d plus a projection matrix times theta small d, right? So now what we are saying is that we are going to split it for every layer in the transformer, right? So that would give you, so forget about lambda I for now. If that is the case, again the equation still remains the same. It's just that you will add a suffix to all the thetas, and the capital D would be reduced by a big margin, right? Because otherwise, let's say if you have 24 layers, your vector will be 24 times of what a single layer would be, right? And and the projection matrix P would be insanely high because of that, right? What they found is that adding a scaling parameter there actually helps them do some things easier, right? So they wanted to add a scaling parameter. Now, if you add a scaling parameter, you're again increasing your space of the vector small d, right? Theta d should be d-dimensional, right? Now if you have d-dimensional there and you have m additional lambda i's, you get d plus m, right? So you don't want to do that. You want to d to be the same, right? So they removed m from the there, right? Okay. Okay, so let's look at, so this notion, so initially it was called intrinsic dimension, now it's called structure aware intrinsic dimension, right? So here what they say is that, so they did this particular way of fine tuning the model and figuring out what is that d that gives you 90% of the accuracy that you would get with full fine tuning, and the number of parameters in the model is listed in the x-axis, right? And the y-axis indicates the intrinsic dimensionality, right? So what we see is that when the number of parameters are small in the model, the intrinsic dimensionality is quite high, right? As you increase the number of parameters, there is a steady decrease in the value of d that is necessary to learn the task, right? So this sort of indicates that the more parameters you have in the model, you have more domain or world knowledge, and the more world knowledge you have, you can learn a task much easier in a lower parameter space than what is needed, right? So this was a very interesting result from this 2021 paper. Now, so let's see here, right? So here what they said was, I have intrinsic dimensionality, which is computationally very difficult to do, and then I have structure aware intrinsic dimensionality. So there are two takeaways here, right? One takeaway is that having structure aware reduces the memory requirements and the train time by quite a bit, right? So you will be able to fine tune much better if you take into account the structural aspects of your network when deciding what you should train and what you should freeze, right? The second point is, if you take into account the structure of the network well, right, then the dimensionality comes down, right? So here for the Microsoft paraphrasing corpus for this task, the dimensionality, when you consider one whole vector without considering the layer wise structure, is 1800, whereas for structure aware it reduces to 1600, right? The dimension itself comes down. You need much lesser parameters to learn, just if you carefully place what you should train and what you should not train, right? So this was a brilliant takeaway from this paper, right? So now, while this was a parallel effort, people did not put in that much thought process into doing this for PEFT. Like they were doing prompt tuning, they were doing prefix tuning because they felt like instead of doing it in the bottom layer, you could do it everywhere. People did adapters, but they were not like giving it much thought about, okay, maybe we should try to reduce the intrinsic dimensionality. Maybe we should worry about what it needs, how do you control this, and so on, right? So that was the base for this LoRA paper, right? So far we know taking into account the structure and then making use of the structure helps, but how exactly to make use of the structure and how do you reduce the parameter space is what LoRA brought in, right? So let's look at regular fine tuning from the view of just weight updates. In regular fine tuning, you would have let's say pre-trained weights, right? And then after training the model and backprop, you will end up getting a weight update del W, and then if you add W and del W, you will end up getting the new weight, which is going to be the fine-tuned weights, right? So now this can be thought of as you're just having two parallel networks, one that goes through the pre-trained weights and one that goes through the recently updated weights, right? And then you can add them, you will end up getting the same thing, right? So what LoRA said was, they made two important contributions. One is they told us what weights you should modify, which will reduce the intrinsic dimensionality by a lot, right? So make use of the structure, and they figured out this is the way in which this is a set of weights in the transformer block that you have to modify. That was one contribution. Second contribution was, how do we represent the del W matrix, right? So this is sort of inspired in the sense that adapters anyway did this, right? They reduced the dimension of the weight matrix by using the bottleneck structure. So they're using that bottleneck structure and basically the del W here is now factorized into BA, one down projection matrix here, and there is an up projection matrix here, right? And there is no nonlinearity, right? Just two projections. So now by doing this, so here FT indicates full fine tuning. Bit fit is a technique that was proposed where you only change the biases in the network and not change the weights, right? That's a trainable parameter. Pre-M is the soft prompting, pre-layer is prefix tuning. Adapters are the same, the Hallsby adapters that I talked about now with different trainable parameters. So what we see here is that LoRa on slightly more complex tasks. Wiki SQL is natural language to SQL. This is a natural language inference task which talks about entailment. This is summarization dataset. So in all these slightly more complex datasets, we see that for a very small fraction of the trainable parameters, you end up getting even slightly better accuracies than full fine tuning, right? So this is the contribution of LoRa. Now, like I said, they also told us what are the parameters in your model that you should update, right? And what they said is that only worry about query, key, value, and the output projection matrix, right? So these are the only 4 weight matrices that you should worry about when you do LoRa. And they also did a lot of aberrations to show that if you keep the number of trainable parameters fixed, right, the rank. If you only train the query vector, the query matrix, then this is the accuracy that you get for SQL, Wiki SQL, and the NLI task. And similarly, if you only train the key matrix and a combinations of query and key, here you reduce the rank because you want to maintain the number of parameters the same, right? And you do all combinations, and they found that in most cases this is a good thing to do, right? So when you define your LoRa config and when you try to fine tune a model, you will have these flexibility with you, right? You will be able to tell the training code, fine tuning code, what matrices that you want to fine tune as a part of this LoRa PEFT, and you can also tell it what rank you want, right? And you would be able to train accordingly. Now they also show like the effect of rank. So basically you can see that the model for various different things, the trend is similar, that you sort of slowly raise up and then you saturate and then you come down slightly. That's the typical trend, right? It's so here if it has not come down, then it sort of, oh no, it has come down already. It has peaked at R equal to 4 and it has come down. So here in some sense the rank here is sort of the intrinsic dimensionality, right? It's not exactly it's not by the definition of what intrinsic dimensionality is, but the rank sort of gives you a control of how much parameters are needed to learn your task, right? And this is one of the most popular PEFT techniques that everybody uses. There is a slight variant of it called QLoRa, which basically the only goal of QLoRa is to reduce the amount of memory needed to do LoRa, right? And and this is one of the most popular techniques that are out there, right? So before wrapping it up, I just want to talk about some more training aspects, which is the A matrix and the B matrix are initialized in a certain way, which will ensure stable training, right? And what they do here is that B is set to 0 for very obvious reason, which is if B is 0, then AB will be 0. If AB is 0, then at the beginning of your epoch, you only have to go through W, right? So your model doesn't change its the way it works, right? You're not adding layers in between. So it's parallel. So this helps in keeping the in preserving the original behavior of the model. Now A is sort of assigned using a Gaussian distribution with 0 mean and a very small variance, and this will also ensure that the way B changes does not throw the model off, right? Because B is going to change drastically now, and if A is randomly initialized, it may throw off, and you would end up having the same issue as what people faced in prefix tuning. So A is initialized in this way so that it doesn't throw off during fine tuning, right? So finally, there are like insane number of extensions to LoRa because it has been so popular. People have explored all varieties of LoRa. QLoRa is one of the most popular technique. There is also long LoRa in case where you have really long context length in your input. There is LoRa Plus, which sort of says that don't use the same learning rate for both A and B matrices in the reparameterization. Use different learning rates and how it will improve the speed with which you can converge, right? And there is also LoRa, which says that with like since R is a hyperparameter, you will have to run your experiments in parallel with different values of R and figure out what works best. But LoRa sort of tells you how to sort of get the right R without running it multiple times. So the intuition here is that they want a del W which can be added to the weight W, right? So there is no, so if you only look at it as a projection, right? So then there is no need for a nonlinearity there to mimic that update of that projection, right? For adapters, it's a different story altogether. You're not trying to add a projection to another projection, right? So here, since you want the LoRa weights to be factorized and added with W, you don't want the nonlinearity here. So the advantage of doing this is that once you train A and B, you can just fuse it to W, right? If you want a single model, right? Again, it will affect all the W's in your network, and you won't be able to do what you did with say prompt tuning, right? Because you cannot easily swap out and swap in, right? So there are also works that are going on for making LoRa as easily swappable as prompt tuning, but you have to do it at a batch level, right? Because you can't have multiple different LoRa's in the same batch. So there is a work around hot swapping in which the amount of time that's required to swap is so less that you won't feel that there is latency there for swapping. But that's the intuition behind nonlinearity in this particular reparameterization.
So
yes.
we are both trainable.
A and B are both trainable. Yes. So I'm not saying it's similar to. All I'm saying is, if your task is complex, it is synonymous. It's not, you can't equate it. Intrinsic dimensionality is not equal to rank, but it's synonymous to intrinsic dimensionality. If your task is difficult and your base language model is also not that good, then you need a bigger R, right? If your base model is good, your task is difficult, you might need slightly middle ground. But if your base model is good, your task is easy, you can even get away with rank 1. All right, I think we are at the end of the lecture. So basically, just to summarize, we covered, in addition to introducing what PEFT is and why we need PEFT, we covered 4 different techniques that are very popular and changed and were like sort of defining moments in this literature. Thank you.